right, welcome back, everybody. We are moving on now to chapter 6. This is going to be the first of two chapters that are devoted to enzymes. All right, so we're going to see enzymes are, of course, essentially important for a lot of biochemical processes. What did we say enzymes are in the first chapter? We said that they are proteins. They're specialized proteins that help to kind of make some of our internal reactions go. All right, so let's give a little bit of background. Again, some of this you are already going to know, but some of it you're not. And so this will be an interesting look at how enzymes work and some different aspects about them. Enzymes, they are biological catalysts. So if you remember the definition of catalyst from any chemistry class, you know a catalyst is something that speeds up a reaction, right? If it's a biological catalyst, that means it speeds up a biologically important catalyst, right? They are, for the most part, made from proteins. There are some very specific RNA examples, but for all intents and purposes, you can think of them as being essentially made out of proteins. They are very, very efficient catalysts. You have, catalysts that we've talked about before, like in organic chemistry or general chemistry. Some of these, you might remember, in organic chemistry, you had a lot of metal catalysts, right? Especially for like catalytic hydrogenation. You had nickel, palladium, platinum. Those were all like just metal surface catalysts. You have acid catalysts sometimes, like sulfuric acid can be an acid catalyst. You can have base catalysts. And they all are good at speeding up a reaction. Enzymes, though, they are super duper efficient, right? Much more efficient a lot of times than non-enzymatic catalysts. You can see here they can increase the rate of reaction by up to over 1,000 times, whereas non-enzymatic catalysts typically increase about 100 times or so. So that's an order of magnitude. Gives you an idea of just how powerful these things are. And you can see I'm going to skip ahead a little bit. Actually, no, I won't. I'll stay in order. Teaching is like telling a story. You got to get everything in the right place, right? So I'll wait till then. Before we get to that part, let's review what basically happens when you catalyze a reaction, right? We've talked about, or you've talked about in previous classes, I'm sure, the concepts of thermodynamics and kinetics, and we did a little bit in chapter 1 as well, right? Thermodynamics has to do with the overall energy favorability. In other words, the delta G, right? The change in Gibbs free energy. We said a reaction was favorable thermodynamically. It was spontaneous if it was exergonic. If you had an overall lowering of Gibbs free energy, from reactants to products. So you wanted a negative delta G. That has absolutely nothing to do at all with kinetics. Kinetics is all about speed. How fast does a reaction go, right? I can't remember if I told you guys this when we met in chapter 1 or not, but if you look at a sheet of paper in front of you, that is actively undergoing a chemical reaction. It's undergoing a combustion reaction. In other words, it's burning. Sheet of paper right in front of you is combusting with oxygen that's present in the air, and it is actively burning the paper, right? Now, it's not burst into flames in front of you or anything, right? In fact, you can't really see much of anything going on. But if you look at paper, like paper that's been in a storage locker or a closet or something for 3 or 4 decades, you look and a lot of times it's kind of yellowed, it's a little bit more brittle, it's kind of curled up a little bit. That's because it's been very, very slowly undergoing a combustion reaction. That reaction is spontaneous. It can happen without any extra help. It's just really, really, really slow, right? If we add something to help it, like a flame, the flame's not a catalyst, but it does add the energy that it needs to actually get the reaction to go faster. What really slows down reactions sometimes is something called energy of activation, and you can see that over here in this photo. There's always going to be a hump a big energy hump that you have to overcome before you can get from your reactants to products, right? Sometimes this is a little hump, sometimes it's a big one, sometimes it's in between. The bigger this hump, the slower the reaction is going to go, right? So if you have a really slow reaction with a high energy of activation, there's a couple of different ways to make it go faster. A, you can give it a whole bunch of energy to help it get over that hump, like adding a flame to a piece of paper, or you can do something to make that hump smaller, right? And this is where a catalyst comes in. A catalyst is going to work by lowering the energy of activation. And how does it do so? Well, basically what it does is the addition of the catalyst makes it easier for the reactants to form the transition state they need to go through in order to get to the products. In terms of enzymes, the way that usually works out is that, remember, enzymes are proteins. So you're going to have a big protein that's going to be folded in a certain conformation, and it's going to have a certain little spot where what we call a substrate, that's the thing binding to it, or the reactants in this case, a substrate can bind to it. It's easier for this substrate to transition and form a transition state when it interacts with this little pocket first, as opposed to doing it by itself. All right? And like I said, it's very, very efficient. I'm going to skip a couple of these. Where am I going? There we go. Sorry for skipping around. I wanted to find this table. We said that catalysts, or enzymatic catalysts, they're really, really efficient. Here's a really, really good example of one. One common reaction that can be done is the decomposition of hydrogen peroxide. I apologize for the lack of subscripts here in my reaction equation. When I transferred files, I guess those didn't translate over, but basically hydrogen peroxide has a formula of H2O2. You guys are all familiar with hydrogen peroxide. You've probably seen it or bought it in like drugstores or something. People use it as an antiseptic, right? A disinfectant for wounds or something. And a common thing that people always report with hydrogen peroxide is you put it in like a cut or something to disinfect it, you'll see it bubbling a little bit, or my mom used to call it boiling, even though it has nothing to do with temperature. But you'll see like a bunch of bubbles, and maybe sometimes some foaming happen, right? The reason for that is because as this reaction as that hydrogen peroxide is breaking down, one of the things that you can make is molecular oxygen, O2, right? Why is it breaking down? Well, there happens to be an enzyme that's present in most animal tissue. It's called catalase. And catalase specifically catalyzes the decomposition of hydrogen peroxide. So if you take some hydrogen peroxide from a bottle, just get a pipette or something and put it on a plastic surface or a test tube or something, it's not going to bubble or boil or anything, but if you put it on skin or on an open cut or something, you'll probably see it bubble some. That's because the catalase that's present in our tissues is actively breaking it down. Okay? By the way, don't ever use more concentrated hydrogen peroxide as a disinfectant. Honestly, even the peroxide that you buy at a store doesn't really work well for disinfectants. You're much better with something alcohol containing. But the hydrogen peroxide you buy at the store is a very, very dilute solution. If you get it much more concentrated than that, it can actually burn you, cause chemical burns. So I've actually gotten burned from 30% hydrogen peroxide before. So that's my public service announcement for the day. You can also catalyze this hypothetically with other catalysts. There's other things that help to catalyze this breakdown, like platinum. Platinum metal is really good at breaking this down as well. However, it's not as good as catalase, right? And so in this little graph, you can see an example of this, the relative rates, right? So if you sort of define the breakdown, the rate of breakdown with no catalyst as being 1, right? That's kind of the average speed that it takes to break down by itself with no catalyst. Adding a platinum catalyst will speed that up by 4 orders of magnitude, right? It'll be over 10,000 times as fast as you would have gotten without a catalyst, which is pretty impressive. But you see, when you add catalase, it will actually catalyze or speed up that reaction by 8 orders of magnitude instead of just 4, right? So that's a pretty big difference. And it does so by lowering that activation energy. And you can see here, you can see sort of get an idea for just how much each one of these different catalysts will do this. And it's a fun little demonstration. You may have done this before. There's a really common demonstration that can be done, like in high school biology classes, or maybe even middle school sometimes, is to get like some chicken from the store, some raw chicken, and get some hydrogen peroxide and drop some of it on the chicken, and you can see it sort of bubble. I've got an even better one that I'm going to show you. And I don't really have to show you this. It's not essential, but I just freaking love this video, and I love showing it to people, so I'm going to show it to you. Brace yourselves. All right, so this wine glass here, that's not wine in it, that is blood. All right, so we got a wine glass that's got some blood in it, and it looks like they're adding some hydrogen peroxide. This is a little stronger than the peroxide that you get at the drugstore for disinfectants or antiseptics, excuse me. This is more the strength that is used commonly for bleaching hair. So you see they're pouring the hydrogen peroxide into the blood, and I'm going to play the movie and let you see what happens.
This is what happens to blood when you mix it with hydrogen peroxide. When we add hydrogen peroxide to blood, it instantly starts to foam, and the reason for this is because blood contains an enzyme called catalase. The catalase enzyme causes the hydrogen peroxide to instantly break down into water and oxygen gas. So the foam that's produced is really just oxygen gas that's being released from the hydrogen peroxide. So that's pretty interesting, but what I really want to show you is how hydrogen peroxide can remove the red color from blood. So this is pork blood, and I'm slowly adding hydrogen peroxide. The very first thing that happens is the hydrogen peroxide will oxidize the hemoglobin in the red blood cells, which makes the red color disappear. Once the red color is gone, we're left with this yellow liquid, which is really just blood plasma. After time, the hydrogen peroxide will also break down the plasma and cause the yellow color to disappear as well.
All right, there you go. Pretty cool, huh? Kind of gross, but pretty interesting as well. I always love showing it like on the big screen, like when I'm teaching a class or something. When I used to teach biochemistry. Sorry, I'm having a hard time finding my windows here. Crud. Alright, so I'm just going to talk aimlessly here while I stall and try to get back to my PowerPoint. So, give me a second. Please feel free to fast forward here because I'm literally just trying to get back to my Moodle page and get my PowerPoint. Something I accidentally closed it. Alright, so come on. So yeah, that's a really fun demonstration to do. It's kind of gross, but it's actually really informative. Another thing that's kind of cool is too that if you cause enough of the hydrogen peroxide to decompose, you can actually take a flame or a little wooden splint that's been lit up, and you can carefully poke it in there, and oxygen is flammable, so you can actually cause it to sort of light up as some of the oxygen burns. So you can have like glowing foamy blood, and that, quite frankly, is just a lot of fun. So, there you go. All right, so sorry for that pause. I had to get back to this. Okay. So, the not so exciting part of enzymes is kinetics, understanding kinetics, and so this goes back to probably stuff that you first started talking about in high school. How do we get the reaction velocity? Well, we can basically look for one of two things. We can either look for the disappearance of reactants or the appearance of products, right? And so that's where this little formula comes from. My iPad does not like the Greek letters, so apologies for those. Again, if you look at the PowerPoint in your on your computer screen, you should be able to see it. But let's say you're reacting A plus B to yield P, right? A and B are the reactants, P is the products. Rate is equal to the negative delta A with respect to time. So that's basically the disappearance of reactant A over time. That's why it's negative. That's also going to be equal to the disappearance or negative delta B with respect to time, which is equal to the positive delta P or product concentration with respect to time, right? So as the products appear, the reactants disappear, right? And sometimes it's really, really easy to track the appearance of a product. Other times it's really, really easy to track the disappearance of a reactant, right? You go with whichever one is the easiest to do from a practical sense. Like, for example, you might have and we're going to take a look at this in a little bit. You might have a reaction in which the reactants are yellow, but as you form product and use up your yellow reactants, the yellow color goes away, right? So in that case, you would probably be monitoring the disappearance of reactants. But it varies according to reaction, which one is easier to measure. All right. For kinetics, when we're measuring reaction rate, we can write rate laws. And this may sound familiar to you. Again, you guys have been doing this since Gen Chem. A rate equation basically tells you, well, number one, it provides a mathematical formula for calculating the actual rate of reaction. But if you look at the formula itself, though, it also gives you an indication of what we call the rate order or reaction order, right? For example, we can have reactions that are first order, second order, third order, zero order, right? The possibilities are endless. However, for your purposes, we'll stick to the most common ones, which are zero order, first order, and second order. All right. Let me get on the whiteboard here to talk a little bit more about this. All right. So, basically, what you're doing when you write a rate law is you're representing the rate of the reaction with respect to the reactants that actually have an effect on the rate. For example, let's just say we're doing this. The same little general reaction we just saw. A plus B yields P. Okay? So, whenever you write a rate equation, a rate law, this part always goes in there. Rate, of course, equals K. This is a rate constant for that particular reaction. These are standard reference values. You should be able to look these up. All right. Then you include the concentration of each reactant that actually makes a difference in the rate. All right. For example, let's say we had let's say we had 1 molar, sorry, this is so ugly, 1 molar reactant A, 1 molar reactant B, and it yields P. Okay? And let's say it yields one product, right? You get When these guys are in this concentration, you get 1 molecule of product. Again, this is just a hypothetical. Let's say we change that. Let's say instead of doing that, we had come on. Oh, still on eraser. 1 molar A, so we kept that the same, but we doubled the concentration of reactant B. All right? So we're going to see, okay, does this actually play a part? Let's say it did. Let's say doubling the concentration of reactant B doubled the amount of product that we got. Whenever you have this direct correlation, like doubling B doubles P, that's a first order relationship. All right? So in this case, with respect to reactant B, this one's first order. Now let's say you did it the opposite way. Let's say we started off with 2 molar reactant A, 1 molar reactant B, and that also gives 2 molecules of product. Then we could say, okay, this one is also first order with regard to reaction A. Doubling the concentration of reactant A doubled the concentration, or doubled the amount of product we get. All right? I'm going to write these down. So we can see the concentrations of A and B are both important. Directly adding more B results in more product. Directly increasing A results in more product. That means you include both of these when writing your rate law. So rate equals K times the concentration of A times the concentration of B. So both of these are included. Each reactant will be raised to a certain exponent. All right? The exponent will match the order with respect to that reactant. Right? So we said that this was first order with respect to A. So the exponent on this one would be 1. Same thing. We said that this was first order with respect to B, so the exponent would be 1 there as well. Most of the time, when the exponent is 1, it's just left off and it's assumed to be 1. So this means the same thing as this, right? Exact same thing. To find the overall rate order, what you do is you add the exponents together. All right, so reactant A has an exponent of 1, reaction B has an exponent of 1. Last I checked, 1 plus 1 equals 2. So this is defined as a second order reaction. All right. You guys have actually seen this before. You guys saw this in organic chemistry. I don't know if you realized it or not. I'll give you an example. Let's look at everybody's favorite thing, nucleophilic substitutions, right? SN2 reactions. Hey, you ever wonder where the 2 in SN2 comes from? That refers to rate order, excuse me. SN2 reactions are second order reactions, right? So for example, let's just put just a general one of these up here. Let's say we had, I don't know, let's say we had 1 bromopropane. Actually, no, I'll draw it the other way. plus OH minus yields this. Okay? So, we would want to say, okay, does this exhibit a second order reaction, right? Well, with this reaction, as you guys learned in organic chemistry, both the concentration of OH minus and the concentration of your alkyl halide are important. Increasing either one of these will directly double the reaction rate, right? That's because both of these things are present in what we call the rate determining step. So that's the mechanism. In order for this product to form, both of these guys have to interact together in what is the only step of this reaction, right? So the reaction rate for this one looks like that. The exponents are 1. 1 plus 1 is 2, so this is a second order reaction. All right. Well, what happens with first order reactions? Let's go back to this. All right, and again, let's say we're starting off with 1 molar of each, and it gives us one molecule product. All right, so let's say we doubled the concentration of reactant B. And that gave us 2 molecules of product, right? We would say, okay, well, again, this one is first order with respect to B. Then let's do the opposite, just like we did last time. Let's increase the concentration of, or double the concentration of reactant A and leave the concentration of reactant B the same. And that makes product, but let's say, oh, that didn't really change anything. Even though we doubled the concentration of A, we didn't get any change in product formation, right? So this would be what we call zero order with respect to A. Okay? Literally has no impact on the reaction at all. So if you're writing the rate law, or rate equation, rate equals K, you only include the reactants that actively change that had an impact on the rate of formation of product, right? So it would be that. The exponent for B is 1, just like we saw before. And if you sum the exponents here, well, the only thing we have is this 1. So that is a first order reaction. And again, you guys have seen this before in organic chemistry, right? We saw this with SN1 reactions. So for example, let's say that we had this, and what do I want to do? I'll just do this. All right, so let's say you had this, and this was your product. All right. All right. So with SN1 reactions, as you saw in organic, these are different because these are 2-step, not just 1. Right. We have to go through. Remember talking about carbocations, right? So this one actually had multiple steps. Cl minus left to make a carbocation. And then the other thing, in this case the acetate ion, can come in and bond to that positive carbon to make product, right? So whereas the SN2 reaction only had 1 step where everything happened at once, this one has 2 distinct steps. In kinetics, you're entirely dependent on the slow step, the slowest step out of all of them that occur. It's what we call the rate determining step. It's just like, if you and a bunch of friends are going somewhere and everybody's ready to go, but except you have that one straggler who you're all waiting on, right? That one straggler slows down everybody in the group. That's kind of what this rate determining step does. And it turns out the formation of the cation, the carbocation, is the rate determining step. It's the slowest step. And that is the only thing that's included when factoring in your rate equation, right? So if we're writing the rate equation for this, it's rate equals K. And you know the alkyl halide is present in that rate determining step. It's the only reactant that's there in that step. The acetate is a reactant, but it doesn't come in until the second step. So it's not involved in that slow step. So as a result, this is a first order reaction. All right. Going to go back to this one more time. All right. So again, we're going to do the same thing. We're going to leave the concentration of A constant, double concentration of B, and let's say that has absolutely no effect whatsoever. All right. Then we do the opposite. Double the concentration of A, leave B constant, and guess what? That does nothing as well. It is possible for none of the reactants at times to have any effect. We could double the concentration of A and or B here all we want. It's not going to impact the rate of formation of product. In that case, literally, your rate equation is just rate equals K. There are no reactants included here, and because no reactants are included here, it's what we call a zero order reaction. All right, let's step back, take a breath. This is all stuff you've probably been over before, but probably got a little bit of rust to knock off because maybe it's been a while since you saw it. Our discussion of kinetics really isn't going to go beyond this. This can get quite a bit more complex as you go up to things above second order, but that doesn't really apply to this situation. So we don't have to go over it. If you ever take PChem, you'll get that much more in depth. But what I want to do is sort of see how this background relates specifically to enzymatically catalyzed processes that occur within biological systems. All right. So I summarized some of this over here, blah, blah, blah. All right, so let's talk a little bit about what actually happens whenever the enzyme works. I referred to this a little bit earlier, right? We said that usually what happens is the enzyme, it's a protein. It'll be folded in a certain way. You'll have a certain pocket at which the substrate or reactant can come in and bind. This spot is called the active site. All right? So the active site sort of helps the substrate form the necessary transition state that it needs to form, right? It helps to do this with a lower amount of activation energy, and then eventually you transform into the product, and then the enzyme releases the product and your reaction is complete, right? That's the very general way of putting it. There's a couple of different models, and again, please keep in mind, it's been a long time since I taught this. These are the models that were present when I was teaching it. These may have evolved since then, but these are the ones that I am aware of. A couple of models for how the substrate and the enzymes interact with each other. The first one is what we call a lock and key model. And that's pretty self-explanatory, actually, right? The active site is the lock, the substrate is the key, and they fit together, right? Very, very complementary. Much like puzzle pieces, they'll be a very good match. The other one, the other model is what we call the induced fit model. All right. So in this case, you have binding of the substrate to the active site in a manner that it fits together with it kinda almost perfectly, but not quite. It's not a perfect puzzle piece match. And then as you get binding, the enzyme will sort of adjust its conformation more to fit it and to get it bound to the active site. And this is actually the one that's a bit more widely accepted these days. Here you can sort of see a visual representation of what I'm talking about. The lock and key model is on the top left, and the induced fit is on the right. And you can see the fit is almost the same as the lock and key, but not quite. All right. When the product is released, you see on the bottom that you have the enzyme substrate complex, but when the substrate undergoes further transformation into product, now the shape is quite a bit different from the shape of the active site, so you're able to get a release. Induced fit is more widely accepted because it is hypothesized that a true lock and key model would almost be too stable. The idea that as that enzyme and substrate bound each other, because they're highly complementary and they fit together just like little puzzle pieces, it might be hard to continue the transformation of product and have that product released. So I think most people will say that the induced fit model is the more widely accepted one. All right. So let's take a look at a couple of examples of enzyme catalyzed reactions. And these are good because you're going to see a stark contrast between them. All right? And it'll also show you why we actually have 2 chapters devoted to enzymes and not just one. All right, first one is going to be chymotrypsin. All right? Chymotrypsin is an enzyme that primarily acts to catalyze the hydrolysis of peptide bonds. In case you're not familiar with the definition of the word hydrolysis, it means when you destroy or break bonds or break molecules apart using water in some way. All right. So this does this to peptide bonds. So, as you might expect, chymotrypsin is actually pretty important in the digestion, of proteins. Right. If you ever eat meat or anything else that has a lot of protein, chymotrypsin is going to be one of the enzymes that helps you break it down. Excuse me. So it's going to break peptide bonds, and it really has a preference for sites within the peptide chain that contain aromatic amino acids. So, tryptophan, tyrosine, phenylalanine, etc. Right? It is also capable of hydrolyzing ester bonds. That's not really that important biologically, but it does make for an excellent little model system. All right, and I'll tell you more about that just in a second. So, for some reason, a couple of the pictures in my original PowerPoint didn't come over whenever I put them on Moodle. I updated it and put a couple of them in, but for this one, I couldn't find the original photos, so I just said, see my video. So this is the video that I'm talking about. So I'm going to show you this on the whiteboard. All right, so we said it's good for a couple of things. Number one, it helps to cleave peptide bonds, right? So if you have something like this, I'm going to just draw a peptide bond. All right, so this is the peptide bond right over here. Chymotrypsin targets this linkage right over there. It likes to snip right between the carbonyl carbon and this nitrogen, right? And again, it really likes to do this when the side chains have aromatic amino acids. All right, and it does so. Oops. There we go. With H2O as a reactant. Not worried about you knowing the mechanism of this, but I am going to show you the end result. So once you split up that peptide bond, typically what you end up with is a carboxylate, right? That's a non-charged, that's a deprotonated carboxylic acid, plus a protonated amine. So this sort of shows you the fate of the two major parts of this peptide bond that exist after it's broken up. All right? Cool. That's what it does to peptides. If you're looking at esters, again, we said this wasn't really biologically that important, but it is going to be important for something else here. So it can also break ester linkages, and it does so very much in the same way, right? I keep drawing that backwards. There we go. So it uses H2O as a reactant, chymotrypsin as the enzymatic catalyst, and you target the linkage between the carbonyl carbon and this oxygen. So much like before, you get a carboxylate ion, and you also get an alcohol as a byproduct, as well as H+. All right. Very good. So, let me see where I am in the show before I get off on a tangent. Oh, yeah. So, why are we talking about esters, right? If we're really concerned about the peptide bonds, why do we care what it does to esters if that's not really biologically important? Well, here's why. We talked about before at the beginning of this video that to measure reaction rate, we got to look for either the appearance of product or the disappearance of reactant. We can't really do that with proteins, with breaking of peptide bonds. There's not really a good, easy way to just, stick a protein in there, stick chymotrypsin in there, and measure the appearance or disappearance of, either reactant or product. It's not easily measured, and we see sometimes, it's not easy to measure either one of these. So what do? Well, if we want to see the activity of the enzyme and how it works, we can often use what we call analog systems. Analogs, models, whatever. We can see how it works on something else that we can measure, and that'll give us an indication of how active that enzyme is. And it just so happens there's a really good reaction that we can catalyze in the lab using chymotrypsin. All right, and it starts off with this guy. This is called para-nitrophenylacetate. Couple of things about this. Number one, lo and behold, it's an ester, right? It's got an ester linkage right over there. Also, this happens to have a color. It's yellow. That'll be important. All right. We can react this with water, catalyzed by chymotrypsin, and it will cause the breakdown through cleavage of that ester linkage right over there. And when it does so, here's what it makes. All right, it actually makes initially this, right? And this corresponds to the alcohol product we saw previously in the general. But usually what we do is we do this in a basic medium. And so once that alcohol forms, it can immediately deprotonate that oxygen. and form that ion. It also makes H plus, two of them, and acetate ion. But the important one is this guy over here. Actually, I guess all of this, now that I think about it. All of this is clear. There's no color to it at all. It's completely colorless. So what happens is, as this reaction proceeds, and you get more and more disappearance of reactant and conversion into product, you see that yellow color start to fade away. You see it start to disappear. How fast this disappears corresponds with the activity of the enzyme. The more active the enzyme is, the faster it'll go, right? So this is a convenient way for us to monitor just how active, in this particular case, chymotrypsin is. And when we do this, we see it looks something like this, right? We end up with sort of a what we call a hyperbolic curve. And so what we've done here is plotted reaction velocity on the y-axis versus substrate concentration on the x-axis. And you can see that the rate of reaction goes up very, very fast, right? With just a little bit of substrate, it goes up pretty quickly, and then it sort of levels off. All right. This is a classic example of what we call a Michaelis-Menten curve, and that this follows what we call Michaelis-Menten kinetics. There's a couple of terms there. I'll get back to them in a little bit. But keep this image in your mind. That's what it looks like for something like chymotrypsin. Now, let's take a look at another one. This is ATCase, which stands for aspartate I can never say this, damn it. Aspartate it's ATCase. I can say carbamyl, but I can't say transcarbamyl. Oh, I guess I just did. Aspartate transcarbamyl lase. Let's just call it ATCase. All right, so basically what this one does, this is a really important metabolic enzyme. Basically what it does is it takes this guy, okay, this is called carbamyl phosphate. And it can react with this guy. This is aspartate. All aspartate is just an aspartic acid where this carboxylate group is deprotonated. So when it's protonated, we call it aspartic acid. When it's deprotonated, we call it aspartate. These two can react with each other. All right, that does so with the help of ATCase. And you get this. And you get some HPO4 minus 2 as a byproduct. Oops, I forgot something here in this top structure. Forgot a carbonyl group. My bad. So basically, this phosphate group gets cleaved off here, off of this carbon, and this group takes its place. And you can form this. This is called carbamyl aspartate. And what it is, this is actually a precursor metabolically for CTP which is cytidine triphosphate, and UTP, which is uracil triphosphate. And these guys are needed for synthesis of nucleic acids like DNA and RNA. So, interesting little factoid there. Essential enzyme. You got to get this together to form carbonyl aspartate in order to sort of start the process that'll eventually lead to DNA and RNA. All right? So, that's fun. What we're really more concerned about right now, as opposed to, we're not necessarily concerned so much with remembering those products. What we're really concerned about is looking at the kinetics. So we can, track this however way we want to. And we see here that the kinetics curve, the curve is different, right? This is a different shape. Whereas before we had a hyperbolic curve where the velocity rapidly increased and then leveled off. In this case, the initial ramping up of the velocity is kind of slow. It takes a little bit to get started. Then it starts to more dramatically increase and then eventually levels off. All right, so this sort of S-shaped curve is what we call a sigmoidal curve. The difference between these two curves is actually pretty similar to what we saw with hemoglobin and myoglobin back in, what was it? Chapter 2, I think. Yeah. So whenever you see this, something like this, this is an example of an enzyme that does not follow what we call Michaelis-Menten kinetics. All right. This is an enzyme that exhibits what we call allosteric effects, and that's really what the next chapter is going to be more about. It's going to be allosteric effects. Allosteric effects are when something can bind to a certain part of an enzyme, and it'll cause a structural shift that'll make that enzyme then either more able to bind a substrate or less able to. Whereas Michaelis-Menten enzymes, they don't exhibit those allosteric effects. All right? So for the rest of the chapter, we're primarily just going to be focusing on the enzymes that are Michaelis-Menten. All right? So I'm going to go into a bit of a discussion of kinetics here, and I'll be honest, there's varying levels to which this discussion can go. I've done this more involved, where I actually go through and do a bunch of mathematical derivations to show you how we get the Michaelis-Menten equation. Hiccups. I'm not going to do that with you guys, number one, honestly, because I think I've found over the years that it just really didn't do much for people. I don't really think it benefited. And then also just because of time here. I think it's a bit of a time sink, so I'm going to sort of skip past that. I am going to show you, first off, some important terms, right? And we can go back over here to this one. We see several terms that are popping up on here, right? We see Vmax. We see Vmax over 2. We see Km. What the heck does all of this mean? All right? Vmax refers to the maximum velocity of the reaction. Eventually, the reaction gets to a point where it doesn't get any faster, right? So that's going to be your Vmax. V naught, or V sub 0, that's what we see in the second bullet point. That 0 should be a subscript, but it didn't take for some reason. That is the initial velocity of the reaction. What is the reaction immediately after you add everything into the system? K sub m. Km, that is defined as the substrate concentration at which we attain 1/2 of our Vmax. Right? So you can see over here in this graph, it's got this sort of measure with the dotted line. When we get to about what our halfway point is on the y-axis as far as reaction velocity, that's our half of our Vmax, we can correlate that with the spot on the x-axis, and that'll tell us what our substrate concentration is at that particular point. I'm not really going to worry about steady state for the moment. Basically what happens here is let me go back to the whiteboard. I'm going to show you basically what we're looking at with regard to a Michaelis-Menten plot. Sorry for the crudeness of my graph here, but it's whiteboard and it's going to look a little wonky. So there's a typical hyperbolic Michaelis-Menten curve. All right. One thing that we see that's interesting here is, okay, substrate concentrations on the bottom, velocity is on the y-axis. This initial part where we see the really sharp rise in Vmax, this exhibits first order kinetics. In other words, the reaction velocity is highly dependent on the concentration of substrate. Right? As that substrate increases as we go from left to right here, we see adding a little bit causes, a pretty big difference. However, once this starts to level out, then this part tends to exhibit zero order kinetics. So, once it reaches this point, we could keep dumping more substrate in. It's not going to help us out any. It's not going to make the reaction go any faster because basically the system is at equilibrium. You've reached something called a steady state. And I mentioned this in the PowerPoint. I'm not going to go too much into this, but at the beginning, you have E plus S. And that forms the enzyme substrate complex. And then the enzyme substrate complex can be converted into product. So basically, when you get here, this is pretty much locked into a steady state. It's not going to change. So that's why adding more substrate just doesn't help any. All right. So when determining, trying to determine things here, like I said, I'm not going to go through the, whoops, I guess I need to go back to my whiteboard. I'm not going to go through the derivation. Feel free to look at it in your book if you are so inclined. I'm certainly not going to ask you anything about derivations on a test or anything, but if you're mathematically minded, you might like looking at it. Basically, we can do a bunch of derivations in order to get something that we call the Michaelis-Menten equation. And this basically allows us to relate the velocity at any given point in that first order portion of the curve to the Vmax, the substrate concentration, and the Km. All right, here's our Michaelis-Menten equation. Okay, and so make a note of this. I think I already told you the definitions of these. The substrate concentration is just basically whatever you're adding to the enzyme, the reactants. Vmax is the maximum velocity, and Km is the concentration of the substrate at which you get to 1/2 Vmax. And then velocity, just V over here, that's the velocity at any given point during that first order portion of the reaction. Okay? So that's a very useful reaction. You can, if you're given some parameters for a particular situation, a particular system, this particular equation can come in very handy. But also, you can use plots. You can use graphs to figure out a lot of these values as well. In fact, what I want to do now is introduce you to another type of plot. We've seen the Michaelis-Menten plot, and it's good for showing, kind of what, these enzymes do. But as far as actually getting exact values, it's not that great because, because it's hyperbolic, it mostly flattens out the top, but actually doesn't flatten out completely. It's still kind of going. Right? There's actually another way of plotting information that gives us something a little bit more exact, and that's called the Lineweaver-Burke plot. And this is actually this is nice because it's a linear plot. It's not a hyperbolic one, it's a linear. So instead of doing this, right, in this case we plotted velocity versus substrate concentration. What we can do is instead plot their inverse values, right? Y-axis is 1 over V, x-axis is 1 over S. And the reason this works is because the x and y intercepts give us direct information relating to the values of Vmax and Km. All right? So here's what, oh shoot. Okay, well, look in your book right now, because my iPad is cutting this off. Look in your book or on a real computer. I am going to do the same. Give me a second while I do this, so I can have the right reference. Okay. There we go. Okay, so if you look at this, whenever we plot 1 over V versus 1 over S, you end up with a linear line. And you can see that it's actually going to intersect with your y-axis, right? That's the y-intercept, right? Where that line touches the y-axis, that's your y-intercept, right? That value is equal to 1 over Vmax, right? So all you have to do is look to see where the line hits the plot, the y-intercept. That's your 1 over Vmax, and then just take the reciprocal, and that gives you your actual value of Vmax. Okay? Also, if you extrapolate your data, right, you can actually extrapolate the data so that this line can continue through your y-intercept, and it can keep on going until it intercepts with the x-axis, right? That's what this little dotted line here is. All right, that's the x-intercept. The x-intercept is equal to the negative inverse of your Km. Sorry, I'm losing my voice a little bit. Excuse me. The negative inverse of your x-intercept. So if you extrapolate that line out and meet your x-intercept, you can pretty easily determine what your Km is. The slope, the formula of the slope is Km over Vmax. All right, and this equation right here shows how all of these sort of relate to each other. This literally is adjusted to the formula for a line, right? Right? This classic line formula that you guys have learned previously. These values fit in nicely for it. One second. Let me get my book. It's actually really simple to take this information and figure out whatever parameter that you're looking for. Let me find the problem that I'm looking for here. Okay, so I'm on page 152 in chapter 6, and I'm looking at a yellow box. It's actually the problem, the problem's entirely on 152. So basically what they do here in this is they give you a series of values, right? The problem says the following data describe an enzyme catalyzed reaction. Plot these results using the Lineweaver-Burke method and determine values for Km and Vmax. The symbol millimolar, that's little m, big M, represents millimoles per liter. 1 millimolar equals 1 times 10 to the negative 3 moles per liter. The concentration of the enzyme is the same in all experiments. So, here's what it gives you. Yeah. So our substrate concentration in millimolar. So you have 5 different measurements, right? We have 2.5, 5.0, 10.0, 15.0, and 20.0. All right. So this was done 5 separate times with 5 separate substrate concentrations. All right. And the velocity was measured at each one of these. And this was in millimolar per second. And this turned out to be 0.024 for the first one, 0.036, 0.053, 0.060, 0.061. All right? And so you're supposed to make a Lineweaver-Burke plot and then figure out what are Vmax and Km. All right. So I would encourage you to do this in a graphing program like Excel or something. I'm just going to sort of hand draw it here just for teaching purposes. All right. So the first thing to realize is if you're doing a Lineweaver-Burke, what do you need? You need 1 over V and 1 over S, right? We don't have that. So the first thing that we got to do is we got to convert these values into their inverses. Luckily, that's done for me in the book, so I don't have to punch these out, but you could easily punch them out on a calculator. All right, so 0.4, 0.2, 0.1, 0.067, 0.050. All right, and then 1 over V, 41.667, 27.778, 18.868, 16.667, and 15.625. All right. So at this point, you got all of the values that you need for your x-axis and your y-axis. So all you would have to do would be to plot them. All right. So again, forgive the crudeness of this. I'm doing this freehand on my iPad, so it's probably going to be a little bit off. All right, so we're going to have 1 over V on the y-axis. So let's start at 0. Let's say 5, 10, 15, 20, 25, 30. Yeah, this is definitely off a little bit, but you get the idea. All right, and this is going to be 1 over the substrate concentration. Again, this is going to be 0, so let's see. 0.05, 0.1, 0.15, 2. Okay. All right, so then all you have to do is start plotting them. So first data point, let's see, it should be 0.4 and 41, so that's going to be somewhere up here. 0.2, 27.7, so right about here. Point 1, 18.8, 0.067, 16.7, something like that. Okay, something like that. Okay, and so then what you would do is you would do a linear regression through these, and boom, there is your y-intercept. So that's going to be about 12, and that's going to be equal to 1 over v. So the inverse of 12, whatever that is. One second. V equals 0.083 millimolar per second. And that's actually the Vmax. Very good. All right. You could extrapolate this a little further and just follow the general shape of the curve or the line down here, and you can figure out what the negative x value would be. I'm looking for it in the book because I already worked it. Haha. X-intercept is negative 0.155. All right, so we take the negative inverse of that. That's Km, and that is 6.45 millimolar. All right, not the most exciting stuff, but it's kind of interesting. And it's actually, despite the intimidating equations in this chapter, once you get down to it, it's pretty easy to do. All right, I'm going to cut this off now because, quite honestly, I forgot to include the portions about inhibitors, and I'm not ready to do that yet without my notes. So I'll make a short part 2 that talks about the effect of inhibitors a little bit later. But this will get you started. If you have any questions, let me know. Bye-bye.